Okay. All of you should have this morning sometime received a Canvas invitation for your next course in the series. Okay, again, it's the classroom portion. As I put in my announcement that I posted last night, it's the classroom portion for the second course of the term, which is advanced air conditioning. Okay, we all know we still have labs to do. That, again, I've laid out the schedule for you guys there on what we're doing in my last night's announcement. Now, the question has come up is part of advanced air conditioning is the EPA certifications. We have received permission from ESCO, which is the organization that actually does the EPA exams. We've received permission to go ahead and give those exams electronically using a Zoom monitored session. So what's going to happen when we come time in that course to give that examination, if we can't get on the campuses by that time yet in small groups or individually, what we're going to do is we're going to have various instructors that are throughout the HVAC department. We're going to schedule times with each one of you that we can maybe do groups of 5 in a Zoom session and give you those exams. The key is that when we give those exams, the camera on your device has to be turned on. Okay, I don't understand why, because it's basically going to be facing the ceiling, but the camera has to be turned on and we have to record that. Just for auditing's sake. The issue with the EPA and the 410A exams is that they are actually, they're considered proctored exams. In other words, we really are not supposed to be giving those without you guys in direct line of sight of an instructor. Well, obviously that's a little tough to do because they're supposed to be closed book. So does that answer the question, Alexander?
Yes, yes.
Okay. Anybody else have a question on the EPA? Okay. So again,
like as a after the when we complete the course, that's for like as a certification, right?
Once you take the exam, you get the EPA certification mailed to you by the testing organization. Okay. It's done by a third party that's actually licensed and registered through the EPA. We just administer the exams. So, again, we have 3 courses each term. You guys are finishing the classroom portion of the core air conditioning on Friday with the written exam. We still have a week of shop we need to do, a week full-time of shop. Okay, that has to wait till the campus reopens. But there's no sense in just having you guys hold off. So we're going to go ahead and we're moving into the advanced air conditioning classroom portion effective Monday. Please accept the Canvas invitation you have so that I know that everyone has acknowledged that they've received it and I know you have access to the new course. Okay. Having said that, the plan for today is I have to talk about pumping down gauges a little bit. And whoever's eating their cereal real loudly or whatever, please put yourself on mute. And yeah, I know who it is, so I don't want to embarrass anybody. But I need to talk about pumping down gauges a little bit today. Now, that's a tough one for me to describe online, so that's, again, something when you get into shop, your shop instructor is going to have more conversation about that and do a demo on it. We also have to talk about 3-phase power today, okay, and 3-phase motors. It is critical that as I go through 3-phase power and 3-phase motors, if you have any questions, ask. Now, I do have a few people in the class who have taken our electrical department curriculum already. They've graduated from electrical as well, and they're now doing HVAC. I do not go into 3-phase nearly as much detail as the electrical department does. The electricians need to know much more about it than we need to know about it. So again, if you're from the electrical department, I may skim over things 1 or 2 times in this. Forgive me, we're not electricians. But if you have any questions that come up, I will get you the answers if I don't know them. So And there is a discussion. There's a post for the day. It's not a discussion board. It's a question of the day. We have one of those today. I believe it's under the three-phase power module. Yes. Okay. And that is your last question of the day for the core air conditioning course. There is not one for tomorrow. Okay. And you'll see that when I post the announcement for tomorrow. Okay, so this is the last question of the day. Make your response good, please. The one other thing that I do want to point out before I get started on the pumping down gauges, I really want most of the people in this class, I want you to look back at the first schematic you submitted to me when we first started this course, and I want you to look at the schematics you're submitting to me in recent assignments. You guys are awesome with the improvement that most of you have made with the schematics. Please, even when we go back, even when you go on to other instructors, don't forget what you've done with the schematics, because you guys are really doing good with them. So that's just a general pat on the back. I'm sort of impressed. Okay. Let's talk about pumping down gauges. Does anybody know what I mean when we talk about pumping down gauges? Can anybody who's maybe had refrigeration before give me sort of a brief synopsis of pumping down gauges? Okay. By what we're meaning is pumping down gauges. We have to be able to remove our refrigerant gauges once they're installed on a system. We have to be able to remove them without losing refrigerant back into the environment. Okay, now there's two reasons for this. One, because the EPA says we have to, and it can come with some pretty hefty fines if we don't. And the second reason is because we don't want to lose that refrigerant out of the system. Remember, your gauges, unless you're using the stubby gauges like I am, okay, this little thing that I just drew as a gauge, it's connected to some pretty long hoses. Okay, these hoses, 4 feet, 5 feet long, usually 4. Okay, there's 2 hoses that are connected to your high and low side gauge that go to the system. Okay, those hoses contain refrigerant. When they're on the system, they contain refrigerant. Okay, different size hoses, different lengths of hoses have different amount of refrigerant in them. But every single time you put hoses on and off a system, you are losing the refrigerant that is in those hoses. Okay? Any questions on that? Okay, so the whole purpose of this is that we have to be able to take these hoses off a system with losing the minimal amount of refrigerant. Now, thinking of where we put these hoses on the system, these gauges, I have a low side hose and I have a high side hose. Okay, we have my compressor up here. Let's just call it C because it's tough to draw with a mouse. We go through my condenser over here. Okay, we go through my metering device. Come out of my metering device, I go through my evaporator. Okay, and I come out of my suction line back to my compressor. In most split systems, in most air conditioning, your low side gauge is going to go there, and your high side gauge is going to go here. Okay, so thinking about your gauges, what is the state of refrigerant that is in your low side gauge?
Vapor.
It's vapor.
Okay.
What is the state of refrigerant that is in your high side hose?
Liquid.
Vapor.
Okay, I heard 2 different answers here. Okay, one was correct. But let me go back here. When you come out of your condenser, what is the state of refrigerant?
Liquid.
Vapor.
Okay, so if I have my high side gauge on my line, the liquid line, coming out of the condenser, what's the state of refrigerant in that gauge?
Liquid.
Okay.
Liquid.
Okay. Everybody understand that? Because somebody did say vapor, and I just want to make sure you got it. Okay. Now, so if I have my gauges on here, my red hose, which is my high side gauge, or whatever color hose, but most often it's red connected to there, is full of liquid. Liquid has more, basically when it boils off, there's more refrigerant lost out of a system. We'll talk much more about that in the next course. But if I lose 10 ounces of liquid compared with 10 ounces of vapor, I'm going to make a bigger impact on the system by losing that 10 ounces of liquid. Okay, because it isn't expanded, it's compressed. Okay, so our goal is we want to lose as little liquid as possible from our gauges. So as I go through this, even though I don't have a set of gauges in my hand like I would normally like to have, I just want everybody to understand my goal is that I want to lose as little liquid through my gauges as humanly possible, okay? That is my whole goal of this thing, lose as little liquid. Okay, now, everyone's gauges or tool bags comes with low-loss fittings. Okay, there are two little brass fittings in your tool bags, and I know I have some new students on here. You haven't gotten your tools yet. Okay, there are two brass fittings that screw into your gauge sets. Okay, Schrader core fittings. Okay. Schrader fittings are the access points on the refrigeration system that look like tire valves. Okay, they have a little core in them that press down and give access to the system. Okay, service valves are not used that often in air conditioning. Okay, the service valves is basically a valve you open and close with a wrench. That is more used in refrigeration. In air conditioning, more often than not, you're going to see Schrader valves. Again, looks like bicycle or car tire air fittings, has a core in it that presses down, and when the core presses down, it gives access to the refrigeration system. Okay, low-loss fittings. Okay, we want to always remove the high side gauge first. Okay. If there's a low pressure switch, we might have to jump out the switch. Okay, again, air conditioning, not that often. Okay, you don't see this that often and it doesn't matter too much. But right now, where I'm at in this, you have your gauges on your system, you're removing your gauges. You've removed the high side gauge from the Schrader port. Okay, and I'll try to do a video of this later on my own system here. And do a demonstration. Now, do I still have refrigerant in these hoses? Okay,
Yes.
Okay, because I have my gauges here. Okay, there's a low side and a high side. The low side is still connected to the system in the suction line. Okay, the high side gauge hose you're holding in your hand, it has that low loss fitting on the end of it. The low-loss fitting prevents the refrigerant from escaping into the air. So all that liquid refrigerant is still in that gauge hose. My low side is connected. Okay, with the system running and the red hose removed, we open the right side manifold gauge. Okay, that's the red. Okay, and what it does, it allows the refrigerant to move into the manifold. Okay. Now, we want to make sure we don't have any air in that yellow hose, because again, air is a bad thing. So we bleed a little bit of air out of that yellow hose. Okay? And again, we're going to have to demonstrate this to you, but I want you to have the basics. Once we know we don't have any air left in that yellow hose, we can open the low side, and we allow the refrigerant to suck into the low side of the system. Because again, remember our gauges, I have very high pressure liquid refrigerant on the red side. Okay, on the high side. And think back to your gauges for those who have them. For those who don't, again, this will be demonstrated to you in the shop. Okay? If the liquid line is closed, the gauges will drop very close to between actually 0 psi if it's a refrigeration system or 60 psi if it's an air conditioning system. Okay, it's going to drop to whatever the low side pressure is. And there's no refrigerant, liquid refrigerant left in those gauges. Again, let's think about what we do with the gauges. Okay, I have two gauges, a low and a high side. My high side hose is full of liquid. My low side is normally a gas, and it's connected to the suction side, which is vapor. If I open a valve to allow the liquid refrigerant out of the high side gauge into the low side and suck into the system on the suction line, okay, all I'm left with in these gauges is vapor. Okay, and it's actually a pretty small quantity of vapor. Now I can take the low side hose off, and all I have left in these hoses is vapor. I'm minimizing the loss of refrigerant. I know some people have to have questions on this. Does anybody have questions? So why do I want to make sure my gauges are pumped down all the time?
So you don't have refrigerant left over in them.
Okay, core reason for that is?
Contamination?
Well, there is a threat of contamination if I go to another system with refrigerant. But my biggest issue is, A, the EPA says I have to, and they can impose a $10,000 fine. And B, I don't want to lose refrigerant out of the system. Those are my two main reasons. Yes, I can have contamination from one system to another. Now, let me ask a follow-up question because I mentioned this yesterday. Once I have only vapor refrigerant in those hoses, okay, I have vapor refrigerant in there. Do I just want to hang the hoses back in my truck and move on to the next call?
No.
Why?
Don't you have to refill the unit again?
Not quite. There was another major reason.
The inside of the
If it gets hot in the van, the gases could expand and blow up the gauges.
That's exactly the issue. Your vans, trucks, whatever you're issued, in a peak summer day is going to get pretty hot. I mean, we hear about it every year when people leave pets and kids in cars. But the reality is that as soon as your gauges are sealed into that truck or car or van or whatever, that inside temperature is going to go up. That 60 psi of vapor that you have in those gauges could easily peak out at over 300 psi by the time you come back and grab those gauges. Okay, so you got to be very, very careful with those gauges. So what do you do with that leftover vapor refrigerant?
You have to bleed.
You have to release it, right? But wait a sec, releasing refrigerant is against the law, isn't it?
Baba.
Yes.
Baba.
Okay, so you release refrigerant. This is what's considered a de minimis release. Okay, de minimis release. You're going to hear about it when we talk about EPA exams and go into the EPA in the next course. Okay, de minimis release is a minor amount of refrigerant that's released from a system that you just cannot avoid. Okay, there's nothing you can do about a little bit of refrigerant that's left over your gauges. It's considered a de minimis release. Okay, don't ask me how much a de minimis release is because there's no definition anywhere on it. But it's considered a de minimis release. It's a release of refrigerant that is totally within EPA guidelines. Okay, but again, it's not, you can't avoid it. So legally, you're not allowed to release refrigerant, but de minimis releases are acceptable according to the law. Okay, so pumping down gauges is all about not releasing large quantities of refrigerant. Now, every refrigerant access point out there comes with caps on it. It's, again, think about a car tire. It's all about covering all possible spots where refrigerant can release. You have no clue how many systems I go on where the caps are not reinstalled on the system. Why is this a bad thing? I want you to think again. Think about the equivalent of the car tire Schrader cap. Why is this a bad thing?
Refrigerant can leak or release?
Yeah, you can have little leaks because there's a little rubber gasket in that Schrader valve that wears out. But there's a few other reasons, too, that are very important. How many people have an air conditioner sitting in your backyard? Or on the side of your house?
I do.
Okay.
I do.
Yeah, a lot of people do. Okay. You ever cut the grass around those air conditioners?
Yeah, you have to.
Yeah. When you cut the grass, are there little blades of grass, little dust, little dirt that's kicked up all over when you're doing that?
Oh, and it goes through the uncapped.
It goes
things.
into the uncapped Schrader fitting. The next time you put your refrigerant hoses on that system, all those contaminants get pulled into the system. On the suction side of the system, there's no filter between that Schrader fitting and the compressor. Okay, so all of those little things end up in the compressor and mixing with the oil. Okay. How many people have dogs that get close to your outside air conditioning unit? Okay. I mean, there's no politically good way to put this, but I see dogs that are peeing on those outside air conditioners all the time. It's a great spot for them to leave their pee mail. Okay, so you have all of those contaminants that can get into that system. Okay, that's why we got to put caps on these systems. Okay, that's pumping down gauges. Again, guys, that is something that is going to have to be demonstrated a little bit in the shop. I don't expect you to memorize that information, but I did just want to cover it a little bit. Okay. Three-phase power. I've brought this up a few times. I've tried to draw you a few diagrams already when we were talking about the sine wave and the out of phase. I did briefly talk about three-phase motors. Do three-phase motors have capacitors? Anybody?
Yeah.
Anybody else? Do three-phase motors have capacitors?
No, they do not.
No, they don't.
Yeah, because we don't. We have three live out of phase leads coming into three-phase motors. So three-phase motors do not need capacitors. Now, will you see capacitors installed on a motor that's on a three-phase system? Yes, because I can run a single-phase motor off of a three-phase power source. We'll talk about that. But primarily, three-phase power is most common in commercial and industrial buildings. You have three hot legs, you will have one ground, and you might have a neutral. Do not count on having a neutral. It's sort of unnecessary. Okay, so again, three-phase power, you will have three hot legs, you'll have one ground, and you might have one neutral wire. Okay, it's not always there. Okay, what color wire is ground?
Green.
Or?
White.
Black.
Solid copper.
Air.
Yeah, it's either going to be green or solid copper or bare wire, no insulation on it. Okay, it will never be white. Okay, that's neutral. Okay, so again, you'll see if you have a neutral, that's going to be a white wire. This will be green or just copper, bare wire. Okay, L1 could be any one of these wire colors, red, black, blue, okay, is our normal colors we use. And it could be in any order. I'll talk more about that, okay? So it might be any one of the three colors, the three primary colors, red, black, and blue, okay? Not necessarily in that order, so you've got to be careful.
What about yellow?
You know, it could be used. I have never seen it used. Because yellow looks to a lot of people awfully close to white. Okay, as yellow fades over time, it turns white. And again, it might be out there, okay? Someplace it might be out there. I've just never seen it. Okay, there's two types of transformer hookups. Now, this is on the feed side. Okay, we come in from the street, okay, and we're bringing in two different types of wiring when we're talking about three-phase power. We have the delta wiring. Anybody can tell me why it's called delta? It looks like the Greek delta symbol.
Delta symbol?
Yeah. Okay, and we have the Y. Okay, why they couldn't call it just Y and had to sort of spell it out, I have no clue. But again, you can always tell them apart because the delta symbol is the delta. It looks like a Y on the Y symbol. Now, what is the main difference between the two when you look at these? What is your biggest difference other than appearance?
Voltage.
Yeah, the delta has a high lag, and can achieve 240 also.
Yeah, you have some differences on voltages. Okay, you have some differences where there's a neutral. Okay, the Y actually has a true neutral in that center point. Okay, your delta does not have a really true neutral. Look at where they're pulling it off. They're pulling it off a center tap. Okay, here we have a true neutral. Okay, and we have the ability to have more 120 volt appliances on here. So there is a real difference in voltage. Okay, and the capabilities of this. Can I get a true 240 volts off of the old delta? Yeah. Okay. Can I get a true 240 volts off of the Y? No. Not possible. I get 208. That's why when you start looking at the higher voltage appliances, the three-phase, it will actually say 240/208 on a lot of your coils and stuff like that. It can be used on either. Okay, there's three basic three-phase power that you're going to encounter. You're going to hit 208 three-phase. That's going to be out of the Y. You're going to hit 240 three-phase. That's going to be out of the delta type windings. And you're going to hit 480 three-phase. That's again out of the Y. Okay, so you're going to have three types of power that you're going to encounter for most of you. Now, occasionally, you're going to go up from there. Okay, I ran across a rooftop system about 2 weeks ago that I was dealing with 720 volts. Okay, so you can go up from there, but primarily this is what you're going to see. Okay, 208, 240, 480. 208 volt is common in newer commercial buildings. Okay, specifically buildings that require power for large equipment but also need a lot of 120 volt circuits. In other words, an office building, we want to have the ability to run our elevators, we want to have our ability to run our air conditioning, we want all the air handlers and everything run off of three-phase power because of the efficiencies of three-phase, but we also need a lot of outlets. Our school buildings, the newer campuses, including Rocky Hill, Waterbury, I believe York has it as well, and Hamden. You guys are running on 208 volt three-phase with the Y windings because of the number of 120 volt circuits. Anything else we get out of that, we're using transformers. Okay? So, power configuration, 208 three-phase. We can have 208 single-phase. I can have 120 volt single-phase, all out of this single power supply. I can get all three of these out of that single power supply. For single-phase power, I'm going to use any one of the two legs. I could use L1 to L2. I could use L2 to L3. I could use L3 to L1. Two hot legs. For the 120 volt, we use one hot leg in neutral. Okay? That's the importance, okay, of the neutral. That's how we get our 120 volts out of a three-phase circuit. Now, in a Y configuration, neutral is more trustable. Okay, it could be grounded properly. In the delta configuration, I never trust neutral. I really don't trust neutral anyway, so I always check it. Okay. So again, this is your Y configuration. Any leg to my neutral, which is my center point, is going to give me 120 volts. Okay, I have my 208 volt here, but again, you can go up in power from 208 and you can get up into the 400s. Okay, that's my Y configuration, 208 volt. I also have 480 volt, three-phase, which is again on the Y configuration. Okay, my 480 volt is common in industrial environments where I have to have higher voltages and also where I have large amounts of fluorescent lighting. Some of the fluorescent lighting in large commercial buildings is not 120 volts. Okay, it's going to be 277 volts. So if someone ever tells you, oh, you can just grab voltage from the lighting circuit to run that air conditioner, don't do it without checking it. Don't do it, period, because it's not quite legal. But you might have 277 volts on the circuit. Okay, now in large industrial buildings, like factory environments, I don't need a ton of 120 volt circuits. Okay, don't need a lot of them because we don't have a lot of computer equipment. We don't have a lot of low voltage equipment, low voltage, 120. Okay, might have a plug here and there for a time clock, coffee maker, radio, something like that, but we don't have a lot of 120 volt circuits. Okay, 480 volt three-phase is made available in industrial applications. Okay, we use them for evaporator fans, we use it for compressors. Sometimes we use 277-volt condenser fans. Not all that often, but sometimes you will see that. Okay. Power configuration that's available off the 480-volt three-phase sources is 480-volt three-phase. We use L1, L2, L3. We can use 277-volt single-phase, L1 to L2, or L2 to L3, or L3 to L1. Now,
if it's the 480 three-phase, it'll never be the Delta configuration, correct?
I don't want to ever say never, but most often. Why don't we say that 99% of the time?
So it's a pretty good assumption that 480 volt means non-delta. You can't use
that's the assumption. That's the assumption I would make.
I would say I've actually heard that it's an older thing that you may see because they've been trying to phase out the deltas.
Yes.
For the power company to actually reconfigure the larger transformers if they have outages, so it's easier for them to work off the Y.
Yeah, that's why I'm sort of going with I don't want to say never, but I want to say the majority. And I agree with that. The companies they're trying to phase out the delta because it is a problem. By the way, that has to be a neat job going and reconfiguring those transformers. Okay. We have to have a separate transformer in the building to supply the 120-volt power. Okay? Once we have a 480 volt, we got to step it down with a separate transformer in the building. Okay? Now, for those of you, I can't tell you where these transformers are in some of your buildings, but for those of you who are in the York building, there's one of these transformers in the electrical supply closet where I went while I was there and did my shopping from the electrical department supplies. For those of you in Waterbury, I think there's a big old electrical supply closet near the back of the building. Hamden has it upstairs, but there's little transformers all around sitting on the floor. And I don't want to say little, these things weigh a ton. But we stepped down the 480 volt three-phase to be able to use 120 volt power. Requires another transformer. Okay, when you're looking at the configuration, do I have 120 volts any place on this Y configuration?
No.
No. Look at that center point. What's the difference between the 208 one that I showed you earlier and the 480 one that I'm showing you now? Look at that center point. What's the difference?
Ground and neutral.
This one is ground. I don't have a neutral. That's why I have to use another transformer. What we do is we take one leg of this and we step it down to a 120 volt with a grounding. Okay, we use another transformer. Okay, when you're looking at a three-phase breaker panel, okay, what we basically have, we have L1, L2, L3. Our main breaker has 3 poles on it. Okay, any breaker that is using three-phase will have a power feed. It will actually attach to the 3 bus bars. We take 2 legs off of this, and we go to another transformer. It steps it down, so then we have 2 legs of pretty standard power, okay, that starts looking more like the breaker panels you're seeing in the house, L1 and L2. Okay, each one of these 2 neutral is going to be close to 115, 120 volts, depending on what the power company is saying. When you go across L1 and L2, I now have single phase 230, 240 volts. Okay, again, someplace in that range. But my main power supply cannot be used directly. I can't just use L1 to ground, or L2 to ground, or L3 to ground. I cannot use that directly to feed appliances and light and circuits such as plugs and stuff like that. So when you have 480 volt or 460 volt power in a building, you are not directly going to feed an outlet. Any questions on this? What's my 277 volt used for mainly?
Fluorescent lights and condenser fans.
Yeah, and less often condenser fans, but more often fluorescent lighting circuits. Be careful with lighting circuits. I've had plenty of building managers try to tell me that rather than call an electrician, I can just run the wire up to the lighting circuit to feed air conditioning units or refrigeration units. And it's not a good idea. Okay? It's not legal, and you might end up with more voltage than you really wanted. Don't be an engineer. Okay, 240 volt three-phase delta winding. There's plenty of these still out there, unfortunately. They're found in older commercial buildings and older industrial buildings. It contains what we call one high leg or a wild leg. Okay, the wild leg is always connected to what we consider phase B in the panel. Okay, and that center leg or wild leg should be orange. Don't trust it. A lot of times what electricians do is they take a red wire or black wire and they wrap orange electrical tape around both ends of it. And that's the signification that it's what we call the wild leg or the center leg. Again, do not trust the markings on this. These are old systems. Wires have faded, marking has gone away. This is, again, why I really... Someone asked about the yellow earlier. Okay, orange could look yellow eventually, will eventually look white. Don't trust these wire colors on this.
So what is the wild leg? Does it have its own control panel? I mean, what does it do?
Let me go through the next couple slides. Okay, its voltages are not 100% the same as the rest. Okay, it has more to do with where the neutral is. Okay, the wild leg to neutral is usually between 180 to 200 volts. In other words, I cannot use that voltage to drive 120 volt appliances, okay? It's not a usable voltage. That's why that has to be marked very specifically, because if I come into a breaker panel, okay, I'm looking at the top of a panel. I have my L1, I have my L2, and I'm just going to put 2 in here, and I have my L3. On an old Delta system, the center one is supposed to be labeled with an orange wire or orange electrical tape wrapped around the wire. Okay, I cannot connect between 2 and neutral, which is off to the side someplace, a neutral bar. I cannot use this. I can't use that voltage. I can go from 1 to neutral and I have usable voltage. I can go to 3 to neutral and I have usable voltage. I cannot go from that lead labeled orange, that's considered the wild leg, to neutral. Okay? Remember when remember that first diagram I put up? Let me see if I can get back to it. Remember that first actually it's coming up on the next slide again. This diagram. Okay? We have to be very careful where we are grabbing our 120 volts from. Looking at this diagram, if I went from L2, L1 to neutral, could I necessarily trust on getting 120 volts?
Isn't that 240?
If I go L, if this is my neutral, L1 to neutral is the only leg that doesn't give me 120 volts. You see it?
Now, my question is, you said that voltage wasn't usable, but I thought that was supposed to be used for things that were 208.
But I can't. I really cannot.
But you know it's with 120, obviously.
Yeah, I can't use it on the 120. Sometimes I can use it on the 208. It's not usable between neutral and we don't want to use it for 120. It's not a usable voltage.
Right.
And again, this is where I sort of need to say, help, I'm not an electrician. That a little bit, the whys of why that is goes over my head. All I know is that that wild leg does not have a usable, you really can't count on the voltage on it. Okay, I wish that's one of those guys, I have to admit, that's not my area of expertise. All I know is basically what I've always been told. Okay. And if anybody who's taken electrical has a better explanation on that wild leg, please say it. I'm fine with you saying it. Okay. Now, that's the three-phase power supplies, but what I am more interested in is what we do with it. Okay? What we do with it in HVAC. In HVAC, is lighting circuits an area where I'm really worried about? Do I really do much of anything with lighting circuits in HVAC?
No.
Should I do anything with lighting circuits in HVAC?
No.
No, your licensing doesn't allow it. Should I be doing anything with outlets in a building in HVAC? Should I be designing electrical outlets? Should I be installing electrical outlets? Should I be repairing electrical outlets?
No. Only in my house.
In your house, you can do what you want to do. Okay, but in somebody else's building, no. Guys, you're not going to be licensed to do that.
Now, I'm just curious, what if something was already wired into the panel and installed on an existing system? Like they had given you a receptacle for convenience. That's kind of then your territory.
As long as it is on my side of the disconnect.
Right.
Okay, now, if you look at newer installations where you have a receptacle outside, sort of in the wall near your outside unit, near the condenser, or in the wall near the furnace. It's there for your convenience because it's required by law to be there. But if it's not wired into the disconnect, okay, if something goes bad with that receptacle, legally you're supposed to call an electrician.
Makes sense.
Okay. Some states are more lenient on that than others. Some municipalities are more lenient on that. I can only go what the state regs basically say, what the International Electrical Code and what the International Mechanical Code says. Some states will say, go ahead, change the outlet out. Some states will say, go ahead and change the disconnect out. Some states, when you change a system out, if you don't have an electrical permit pulled on that disconnect, they're going to fail the inspection because you didn't have an electrician come out and check it. Okay? Massachusetts is famous for this. Every little town has a different rule. And if you know the building inspector, and once the building inspector starts seeing your work, they're going to give you a little bit of leniency. The first time they look at your work, you can't pull a thermostat wire in Massachusetts from the basement to the second floor without having an electrician involved. Wiring is an electrician's territory. Okay, Connecticut is a little looser on that as long as you have the proper license to do it. Okay, but different states are different things. Down here in Florida, I'm supposed to call an electrician for everything. Okay, but I know most of the building officials, they've seen my work, and go pull an electrical permit on it. We want the money. And then they let me get away with it. So different states have different things, and again, as the inspectors start seeing the quality of your work, they'll let you do more and more. Okay. Three-phase motors, they are more reliable and more dependable than any other type of motor on the market. They're very rugged. They can stand up to more. They can stand up to a lot of different conditions, temperature-wise, power-wise, and everything else like that. They're a much better motor than any other type of motor on the market. Okay, now I'm going to put one note in here, okay, that I want you guys to realize. These slides were written about 4 or 5 years ago. There's a new type of motor on the market that's becoming more and more popular. It's an ECM motor. Okay, ECM, electronically communicated motor. Okay, it takes the AC current and it changes it to DC by the time it gets to the motor. Okay, so my statement about more dependable, reliable than any other type of motor excludes ECM motors that we're starting to see in a lot of residential equipment. Okay, ECM motors are awesome because they're DC motors, and DC motors last a long time. Okay, so just be aware of that, that my reliable, more dependable than any other type of motor excludes ECM motors. That's a whole separate conversation. Okay, three-phase motors are much stronger than single-phase motors. Okay, they have a lot of strength to them because of the 3 phases of power that's coming into it. Three-phase motors don't require starting components. Okay, don't require any starting components whatsoever. Three-phase motors are able to start heavy loads. Okay, large compressors, large pieces of equipment can be started and stopped with three-phase motors. Can I use a three-phase motor on a small air conditioner? Of course I can. Okay, but we tend to see them in heavier loads because three-phase power is not available in most residential buildings. I wish it was, but it's not. So single-phase motor power looks like this. Okay, single-phase has this appearance. Okay, single sine wave. I have my L1 that grabs power here. I have my L2 here. Things are set up a little bit differently. I have neutral in the center. Single phase, it goes through neutral, which is an effective 0 voltage. How many times a second does it go through neutral?
60.
Well, that's my entire cycle. Okay, it starts off at neutral. It goes through neutral in the center and returns to neutral. So basically, it goes through neutral once here and once when we're finishing. Okay, and then we start the next thing. So we're actually hitting we're hitting it more often than 60 times a second. I'm hitting the center one 60 times a second, but what about this one right there? So basically, we're actually going through neutral 120 times each second, because a whole 360-degree cycle, okay, is 60 times a second. But regardless, so this many times a second, I do not have voltage. Okay, now granted, this is a small slice in time. Okay, but I don't have voltage. I have no difference in potential. Our motors lose efficiency. Yes, I can use a start cap, or I can use a start winding to slightly give me another phase. Okay, but it's not as reliable as having a true three-phase circuit. Looking at this chart, are any two legs of my three-phase circuit in 0 at the same time?
No.
So I always have a difference in potential, because if L2 we'll call this, if it's at 0 right there, I can draw, well, if I had a ruler, I could draw a straight line, and none of my other phases would be in neutral or 0 at the same time. So I always have a difference in potential between there and there, there and there, and there and there. Or my red, sorry. Okay, I always have a difference in potential. So my motor windings, do they ever have a total collapse of magnetism? Do my motor windings ever totally collapse in terms of magnetism? Do I always have a north and south? Yeah, I'm always going to have magnetism on the winding because I'm always going to have a winding with AC power going through it. Okay, that's the whole premise of three-phase motors. You always have magnetism in the windings. There's never a point in time where I could have a collapse of the magnetism. So the motor's constantly getting power. Okay? Three-phase power supply has to have it. Okay? I can't use single-phase power on a three-phase motor. It's not happening. I have two types of motors. I have a single voltage motor or I have a dual voltage motor. A single voltage motor has 3 wires. It's specifically designed for a single voltage. Dual voltage motors have 6 to 9 wires. We'll go through this in a minute, the different configurations. This allows me to have one motor that I can keep on my truck or in a supply house someplace that has many voltages that I can wire it for, depending on how I connect wires. The stator in the motor has 3 separate windings. They're always 120 degrees apart. Makes sense because 3 times 120 is 360. The way it's wired, the way it's wound, those windings are 120 degrees apart electrically. The windings are either wired in a delta or in a Y configuration. Here's our delta and Y again. Now, this is the key. All 3 windings have the same resistance reading. I drew this out about a week ago, I think, when we were talking about motors. Okay? Remember, in a regular motor, we have a start, run, and a common. Okay, the start winding has greater resistance than the run winding. Okay, in three-phase power, okay, I have 3 different windings. They all have the same resistance. If the motor runs backwards, which happens occasionally when you first connect a three-phase motor, just reverse any 2 leads. In other words, if you connect a three-phase motor to an air conditioner and it starts running backwards, you can either see it or hear it, you're just going to take L1 and L2 and reverse them, and it will fix the problem. Okay? Actually, both of these points are very possible test questions because it's so important. In a 3-phase motor, all the windings have the same ohm reading. To reverse rotation, in other words, if your motor's running backwards, reverse any of the 2 leads. That's the importance.
What's the reverse any 2 leads means?
As I just said, if you take L1 and L2 and you just swap them. Okay, if you have L1 connected to one wire, L2 connected to another wire, you just swap them.
Oh, okay.
Doesn't really matter because the motors, all the windings have the same ohm reading. The problem is the way it's wired internally to the motor, okay, it may just have, maybe on the wrong phase. It happens. The power coming into the building may not have been set up correctly. It happens. Okay? When we look at these windings, can everybody see why one's a delta and one's a Y? Again, we have our delta symbol. Over here we have our Y symbol. Now, both of these motors are a dual speed motor. Okay? It all depends on how you connect these connections on what the voltages are. Sorry, dual voltage. Okay, so you might have to connect power to 1, 7, 3, and 9, 2 and 8, or you might be told to connect 6 and 9 together, 4 and 7 together, 5 and 8 together, and connect your L1, L2, and L3 to just my 1, 2, and 3. That's all very important. It's on the motor label. Makes a big difference in voltages. Okay? So on the motor label, I may have one for high voltage connections. And by the way, these are pretty standardized. So if you grab this PowerPoint handout, it might be a good slide to keep. These are pretty standard, but they're always on the labels. So if we're using high voltage, which like would be 460 volts, I would connect these terminals together. Actually, not that, sorry. I'd connect the terminals together. I'm being told to connect together. So my 7 and 4, you see it's connected. My 5 and 8 is connected. My 6 and 9 is connected. That's this series right here. Then I'm being told to bring L1, L2, and L3 into 1, 2, and 3. Okay, which is right here, and right here. That's my high voltage connections. Now this motor would be running on 460 volts. Okay, low voltage becomes a little bit more interesting. So this might be like 208. Okay, so low voltage, you now are going to connect pins 5, 6, and 4 together. You see how that's jumped right there? 5, 6, and 4. They're just wire nutted together. And then you're going to bring your voltages into, your L1's going to come into 1 and 7. Your L2 is going to come into 2 and 8. Your L3 is going to come into 3 and 9. What did we just do there? What happened to those windings when we went from the high voltage to the low voltage setup? What did we do? Look at this electrically. What did we do?
You disconnected the 6 from the 9, the 5 from the 8, the 4 from the 7, and instead connected the 6, 5, and 4 together and threw in the 9, the 8, and the 7 into the line voltage.
Okay, but what did it do to the windings? Are they now do I have a second basic set of windings connected in parallel to the first?
Yeah.
Yeah, that's where I was going. When you go to the low voltage configuration, I now have 2 complete sets of windings, okay, that are in parallel to each other. Okay, so I could be increasing the strength of the motor by putting another set of windings in parallel using the lower voltages. Which is going to draw more amperage? The first configuration or the second configuration? Which draws more amperage?
One thing that I definitely want to talk about is
the second configuration is going to draw more amperage. Okay, the first configuration is going to actually be a more efficient motor. The higher the voltages, the longer the windings. The second configuration is going to draw more amperage. Somebody asked a question and I didn't hear your entire question. Or it might have been accidental. Okay, delta windings have the same possibility. Okay, delta wound high voltage. Look again at what we're doing here. We're basically making longer windings. Okay, in the delta pattern. The low voltage, again, now I have two deltas. I have one there, and I have one there. Not a really neat looking delta, but close enough. Okay, so again, I'm connecting. In the high voltage, we have longer windings. In the low voltage, I have shorter windings, but I basically have two sets in parallel with each other. Okay, but again, these motors are neat because you can actually have one motor with two voltage configurations. Guys, these two slides, I would really recommend that you download the handouts or download the PowerPoint and save these two slides. I took an electrical certification test a few years ago, and I actually had a hard time finding these. And they're on the motor labels. They're with the handouts that come with motors a lot of times. But over time, those things get lost. And these are once you know what you're looking at, you can actually use an ohm meter and find the different windings, find the different pins. Does anybody have a question on this? Anybody have a question on anything that I covered today other than that wild leg, which I will go to one of our electrical instructors and see if I can find you more information on that. Okay. Okay. So let's look at where we are in this course right now. Okay. We're going to a little bit talk about troubleshooting motors tomorrow, okay? I've gone over so much of it already as we've been doing our lessons. I want to talk a little bit about troubleshooting motors tomorrow. I want to talk a little bit about wire sizing tomorrow. Wire sizing won't be on the final, but I do need to cover it. And then on Friday is your final exam, okay? I'm going to try to keep tomorrow as short as humanly possible. We've been running about an hour or so. I want to keep tomorrow as short as humanly possible because I want to give you guys plenty of time to get work turned in, plenty of time to do some studying for the final. If you have questions on what's on the final, I did a little bit go over a few things yesterday on our lecture, so if you didn't pay attention yesterday, please watch the recording. All work must be submitted to me by midnight on Friday, basically, which is coming up to us shortly. If there's assignments that are closed that you can't access anymore, it's probably discussion boards or assignments of the day. Guess what? Assignments of the day were due that day. You can send it to me. I'll try to do something, but you're not going to get full credit. Pretty much all of you guys are doing well on work caught up, so I'm not really worried about it. But does anybody have any questions about this course or what we're doing over the next couple days? If you have something you want to ask me not in this session, please email it to me. I'll get to it later this afternoon. So everybody can have a great rest of the day. Thank you very much for your time, and I'll